I'd like to talk a little bit more about logical equivalence and at the same time introduce a couple of new logical connectors to you. You've probably seen some of these before. Let's consider one over here, very well known one. It's called exclusive OR. And that is written very frequently. It's written this way. I don't believe this is in your book, but we should talk about it nonetheless. And what exclusive OR basically means is that this statement is true when either one of A or B is true, but not the case when they're both true. So it has to be the case that just one of them is true. So we could come over here and we could draw a truth table for this. And with two variables, we know we're going to have 4 rows here. And remember, we said that this is true only when one of them is true. So it's going to be true in these two situations right here. And it's going to be false in these situations right here. Now, this truth table actually gives us an opportunity to look for a logically equivalent way of expressing A or B. Notice A exclusive or B. Notice that A exclusive or B is true in this situation here. And notice that that situation there corresponds to not A and B. Remember, if A is false, then not A is true. And if B is true, then B is true. And notice in this situation over here, and that situation corresponds to A being true. And if B is false, okay, so this would be A and not B. Does everybody get that? Notice over here, if A is false, not A is true. B is true, B is true. I come over here. This expression over here corresponds to this expression right over here. Now notice exclusive OR we are saying is true. It's either true in this situation here or in this situation here. So we can come up with a logical equivalence right over here and say that exclusive OR is equivalent to not A and B, or A and not B. And basically, we can do this for any logical connector, for any logical expression. We go ahead and we build the truth table. We just find the rows that are true, and we OR them together. And that's exactly what we did over here. I'd like to talk about another interesting logical connector, and it is called NAND. So I come over here and I'm going to say A NAND B. And NAND just means not and. So A NAND B is equivalent to saying not A and B. And again, you may recall from De Morgan's rule, which we've seen a while ago, this is actually equivalent to, and this should be like that. This would be not A or not B. So let's first of all draw a truth table for this. So if I have A and I have B and I have A NAND B, well, we know that A and B would be true over here and false everywhere else. So if we're going to say not and, we have to flip all of that, and this is false, and that would be true, and that would be true, and that would be true. So I want to consider a couple of things here. First of all, I'd like to consider, what is A NAND A? Okay, well, A NAND A, remember this is equal to not A and A. So first of all, we can see over here, if A is true, then A and A would be true, and not true would be false. So if A is true, then A NAND A would be false. Likewise, if A is false, false and false would be false, and to flip it around would make it true. So one of the things that we can see right here is we can see that basically A NAND A, it goes from false to true, and it goes from true to false. This does the same thing as not A. Very interesting. Okay, let's look at another example here. Suppose I were to say A NAND A, and I were to NAND that with B NAND B. Well, first of all, we've just shown that A NAND A, this is not A. NAND, and B NAND B would be not B. So this over here would be not A and not B. But by De Morgan's rule, I'm going to distribute this over here, and that's going to give me the same thing as A or B. Okay, so A NAND A, NAND B NAND B is the same thing as A or B. The other interesting thing to note here is let's consider the following. Suppose I went A NAND B, NAND A NAND B. Okay, now notice both of these terms are exactly the same. They both say A NAND B, okay? And what we can do is we notice that basically what this is this would be equivalent to not A NAND B. Okay, but A NAND B would be equivalent to not A and B. And these two knots would cancel each other out, and I would just get A and B. So there's an interesting thing to note here. With this thing called NAND, I am able to implement negation. I am also able to implement OR, and I'm also able to implement AND. Some people will say that NAND is what's referred to as a universal operator. And the reason why it's referred to as a universal operator, I think we've demonstrated it here, is that we can implement AND, OR, and NOT just using NAND. That's a very interesting property and a very powerful property. There's another operator, and I'll leave this as a homework assignment, okay? There's what's called the NOR operator. A nor B. And that's equivalent to not A or B. And it turns out that that is also a universal operator, which means that just by using NOR, I can implement NOT, I can implement AND I can implement OR. And I leave it as a homework exercise for you all to try this out. Okay, to finish up section 2.1, we want to return to something that is mentioned in your book. They started off the chapter this way. I've intentionally left it to the end, but it's the whole idea of translation. And what I mean by translation is taking something that is stated in English and translating it into the propositional logic. And there are a couple of examples that they mentioned in the book that I think that are worth mentioning. Suppose I were to say to you that suppose I were to say it's sunny but cold. And the key word here that we're focusing in on here is the word but. Okay? And you can think of the word but as actually meaning and. If I were to say to you it's sunny but cold, I am actually saying to you it's sunny and cold. I don't think that comes as a surprise to anyone, but people don't often think of the word but and as meaning the same thing. The other example that they provide in the book that is also worth mentioning is consider the following sentence. I have neither apples nor oranges. Now, think about what this statement is saying here. If I were to let A equal the statement, I have apples, and I were to let B be the statement that I have oranges, what I am basically saying over here is I am saying not A and not B. So the construct that we're looking at here is this neither nor. Okay? I think that's the end of chapter 2.1. Start reading and doing homework.